Good evening, welcome back, or if this is your first time here, welcome. Tonight we're going to explore something that connects you to these words right now, something so invisible you probably don't think about it, yet it's woven through nearly every moment of modern life. We'll discover how the internet evolved, slowly and patiently, from a secret military network connecting just 4 computers to the vast invisible web that now links billions of devices worldwide, carrying your messages, your videos, your entire digital existence across continents in fractions of seconds. We'll begin in the 1960s with researchers frustrated by slow mail and unreliable phone lines. Stand beside the engineers who built ARPANET's first connection between UCLA and Stanford. Watch the invention of TCP/IP protocols that let different networks finally speak to each other, and follow the quiet revolution of email file transfers and the domain name system that transformed incomprehensible numbers into friendly names like google.com. If this story helps you rest tonight, feel free to like or subscribe, though there's no pressure. I'm always curious where you're listening from, so if you feel like it, comment your city and what time it is there. Perhaps you're reading this on a smartphone connected by cellular towers and fibre optic cables you'll never see, or perhaps on a computer linked through copper wires installed decades ago, the invisible infrastructure carrying these words to you right now. Dim the lights now if you haven't already. Adjust your pillow, finding that comfortable position. Maybe turn on a fan for some gentle white noise, or simply let the quiet settle around you like the darkness in a server room at night, where machines hum steadily, maintaining connections you never think about. We have decades of networking history ahead of us, but we'll take it slowly, one protocol at a time, one cable connection after another, the patient accumulation of technology that makes the modern world possible. Let's begin. Imagine you are sitting in a university research office in 1968, perhaps at MIT or UCLA or Stanford, one of the major American research institutions receiving government funding for scientific work. The office smells of typewriter ribbon and strong coffee gone lukewarm in ceramic mugs, of paper stacked on every surface, of the particular mustiness of old buildings with inadequate ventilation. The window shows a campus quad, students walking between buildings, the late afternoon sun creating long shadows across maintained lawns. You're a researcher working on computer science, though that term is still relatively new, the field being barely a decade old as a formal discipline. Your work requires collaboration with colleagues at other universities, sharing research findings, discussing problems, coordinating on joint projects. But communication is frustratingly slow, maddeningly unreliable, expensive enough that budgets limit how often you can contact distant colleagues. The telephone sits on your desk, heavy black bakelite, rotary dial, the handset's spiral cord coiled and recoiled thousands of times. You can call colleagues across the country, but long-distance rates are substantial, your department watching the phone bills carefully, questioning excessive usage. And telephone conversations are ephemeral, gone the moment they end, requiring careful note-taking, the scribbled reminders on yellow legal pads being your only record of what was discussed. For sharing actual research data, actual computer programs or results, the telephone is useless. You need to send physical documents, actual paper, through the postal system. You type your findings on an IBM Selectric typewriter, the satisfying click-clack of keys striking paper, the ding at the end of each line, the mechanical return carriage swooshing back to begin the next line. The smell of typewriter correction fluid hangs in the air when you fix mistakes, white liquid brushed over errors, waiting for it to dry before typing the correction. Making copies requires carbon paper between sheets. the blue-black film transferring impressions to pages beneath, your fingers getting smudged with carbon residue, up to perhaps 6 copies being the maximum before the bottom copies become too faint to read clearly. Or you use the mimeograph machine down the hall, cranking the handle to force ink through a stencil, the purple-blue copies coming out damp and smelling of solvent, the distinctive mimeograph smell that will linger in your memory for decades. The documents go into manila envelopes, addresses typed on labels, postage stamps affixed, dropped into the mail slot. Then you wait. Domestic mail might take 3 to 5 days, letters to colleagues in California being about a week from Massachusetts, the cross-country journey happening at the speed of trains and airplanes sorting mail. International mail is even slower, weeks between continents, a letter to a colleague in London requiring 2 weeks minimum, sometimes 3 or 4 if postal systems are backed up or if the letter gets misdirected. And while you wait for replies, work stalls. Questions remain unanswered. Errors in your code or methodology go uncorrected. Collaboration happens in geologic time, measured in weeks and months rather than hours and minutes, the friction of distance and delay being so great that you often work alone rather than coordinate. Isolation being easier than the painful slowness of remote collaboration. The computer you use is a mainframe, a room-sized machine operated by specialists accessed through terminals in your office. Time on the computer is rationed, scheduled in advance, your programs submitted as decks of punched cards, the rectangular cards with holes encoding your program's instructions. The cards are heavy in your hands, stiff cardstock, the corners slightly sharp, the distinctive smell of the cards being a mix of paper and machine oil from the card readers. You carry your card deck to the computer centre, hand it to the operator behind the counter, receive a claim ticket, told to come back in a few hours or tomorrow to collect your output. The waiting is substantial, multiple people's jobs being queued, executed one after another, the mainframe's time being too precious to waste. When your results are ready, they're printed on continuous form paper, green bar paper with perforated edges. The dot matrix printers were having produced your output, which might be exactly what you wanted or might reveal an error requiring you to correct your card deck and submit again, the cycle repeating. The idea of sharing data with a colleague's computer at a different university is almost science fiction. Your computers are incompatible, running different operating systems, using different data formats. Even if you could somehow connect them with phone lines, they wouldn't know how to talk to each other, the machines being islands, isolated, each installation being unique, local, disconnected from the broader world. This isolation feels increasingly problematic as the 1960s progress. The government is funding computer research at multiple universities, the Department of Defense in particular supporting projects it thinks might have military applications. But the computers can't share data, can't coordinate, can't form a network. Each is a standalone system, its knowledge and capabilities locked within that one location, unavailable elsewhere. Military planners have an additional concern, one driven by Cold War anxieties. The telephone network, as it exists in the 1960s, is fragile in specific ways. It uses circuit switching, meaning when you make a call, a dedicated physical circuit is established between you and the person you're calling, maintained for the duration of the call, resources committed even when neither of you is speaking, just dead air-consuming capacity. More worryingly, from a military perspective, the telephone network has centralized switching points, vulnerable nodes whose destruction would sever large sections of the network. A nuclear strike on major cities would likely destroy telephone exchanges, cutting communications across vast regions. The military wants a more resilient communication system, one that could survive partial destruction, that could route around damage, that wouldn't fail completely if some nodes were eliminated. These various pressures converge, creating the conditions for innovation. The Advanced Research Projects Agency, ARPA, a Department of Defense agency created after the Soviet Union launched Sputnik, begins funding research into computer networking. The goal is creating a network connecting research computers at various universities, allowing them to share resources, share data, and demonstrating survivable communications technology that might have military applications. Years pass. You now find yourself standing in a computer lab at UCLA in the basement of Boulter Hall. October 29, 1969, late evening. The room is warm despite the air conditioning labouring to cool the equipment, the smell being a mixture of warm electronics, the ozone produced by electrical equipment, the faint mustiness of the basement, and the ever-present coffee from a pot that's been reheating all day on a hot plate. The coffee by now thick and bitter. The interface message processor, the IMP, sits against one wall, a refrigerator-sized box, battleship grey, panels of blinking lights showing its operational status, lights that flash in patterns as the machine processes data. This is the first IMP, node number 1, of what will become ARPANET, delivered by Bolt, Beranek and Newman, the consulting firm that won the contract to build these specialized computers that will serve as the network's routers, directing traffic between nodes. The IMP connects to the host computer, an SDS Sigma 7, and also to a telephone line, a dedicated 50 kilobit per second circuit leased from AT&T, running south to Stanford Research Institute in Menlo Park, roughly 400 miles away. The phone company installed special equipment to carry data rather than voice, the line being expensive, the monthly cost being substantial, the government funding being necessary to afford such experimental infrastructure. You're part of the team attempting the first network connection, the first communication between these two nodes. The plan is simple. Log into the Stanford computer remotely from UCLA, typing login on the UCLA terminal, watching those letters travel through the IMP, down the phone line to Stanford's IMP, to their host computer, demonstrating that the network works, that computers separated by hundreds of miles can communicate. The terminal is a teletype machine, essentially an electric typewriter connected to the computer, the keys heavy and mechanical, each keystroke producing both a printed character on the paper roll and an electrical signal sent to the computer. The sound is distinctive, the click-clack of keys being struck, the whir of the motor advancing the paper, the mechanical return bell dinging when approaching the margin, sounds that will become associated with early computing, the acoustic environment of programming before silent keyboards. The researcher at the terminal types L, silent keyboard. The letter appears on the local paper, and through the magic of this new network, should appear on Stanford's terminal as well. You watch the phone line status lights on the IMP, seeing activity, seeing the packet being sent. From Stanford, via a separate voice phone line used for coordination, comes confirmation. They received the L. It worked. The researcher types O. Again, success. The O arrives at Stanford. 2 letters transmitted successfully across 400 miles, the data travelling as electrical pulses on copper phone lines routed through these new IMP machines, using a revolutionary technique called packet switching. The researcher types G, intending to complete login, but the system crashes. Stanford's computer, overwhelmed by this novel network traffic, by the unexpected data format, freezes, stops responding. The first message sent across the ARPANET was "Hello" before the system collapsed, an inadvertent poetry, "Hello, being almost biblical, the greeting before the announcement, before "Behold." Though the first attempt ended in disruption, a complete login followed within an hour after reboots and adjustments, the subsequent success being less poetic but more functional, the network proving itself capable even if fragile, even if prone to unexpected problems, even if requiring patience and debugging and constant attention from its creators. The technology underlying this connection is packet switching, a concept that seems simple in retrospect but was revolutionary in 1969. Instead of establishing a dedicated circuit for the duration of a communication session as the telephone network does, packet switching breaks messages into small packets, each packet containing data plus addressing information. Each packet being independently routed through the network, potentially taking different paths, arriving possibly out of order, being reassembled at the destination. The advantages are multiple and profound. Packets can route around failures, taking alternative paths if one route is blocked or broken, the network being resilient to damage, surviving the loss of individual nodes or connections. The network uses bandwidth efficiently, filling available capacity with whatever packets are ready to send rather than holding circuits open during silence. And packet switching allows multiple concurrent conversations to share the same physical links. Statistical multiplexing meaning that the combined traffic of many users can flow through shared infrastructure rather than requiring dedicated circuits for each connection. The interface message processors themselves are modified. Honeywell DP516 computers, mini-computers small enough to fit in a rack, specialized machines whose job is receiving packets from attached host computers or from network connections, examining the destination addresses, consulting routing tables, forwarding packets toward their destinations. The first routers, though, that term wouldn't be used for years, these being the ancestors of the Cisco and Juniper routers that will eventually handle internet traffic worldwide. The network grows slowly through late 1969 and into 1970. Additional nodes being added, UC Santa Barbara receiving the third IMP, University of Utah getting the fourth, the network becoming a network rather than just a point-to-point link, the topology allowing multiple paths, the routing algorithms becoming meaningful when there are choices to make. The daily work of using ARPANET settles into rhythms. Researchers log into remote computers, accessing computational resources they don't have locally, running programs on distant machines. The novelty of remote computing gradually becoming normal, becoming expected, the magic wearing off as it becomes utility. The teletype printers clack continuously, printing incoming messages, the distinctive sound becoming associated with network traffic, the quiet periods being notable absences of activity. File transfers happen, research data being sent between institutions, the FTP protocol being developed to standardize this process, the file transfer protocol becoming one of ARPANET's killer applications, the ability to move data files electronically rather than mailing magnetic tapes being transformative for collaborative research, the speed and convenience reshaping how science happens. Time passes. You now find yourself at Stanford University in the mid-1970s, working with Vint Cerf and Bob Kahn, who are developing something they call TCP/IP, a pair of protocols designed to solve ARPANET's scaling limitations, to enable internet working, connecting different networks together, creating a network of networks, an internet. The problem is that ARPANET's network control protocol works well within a single network, but doesn't handle the emerging reality of multiple different networks using different technologies. There are packet radio networks for mobile military units, satellite networks for long-distance communication, various local networks at different institutions, and they're all incompatible, unable to exchange traffic, isolated from each other, creating islands rather than an integrated communication infrastructure. Cerf and CERN are proposing a solution, a two-layer protocol system. The Internet Protocol, IP, would handle addressing and routing, providing a common addressing scheme that works across different network technologies, allowing packets to traverse multiple different networks on their journey from source to destination. The Transmission Control Protocol, TCP, would sit above IP, providing reliable end-to-end communication, handling packet loss and reordering, ensuring that applications receive complete, accurate data even when the underlying networks occasionally lose packets or deliver them out of sequence. You're in a computer lab, the smell of warm electronics and stale coffee being familiar, the hum of air conditioning fighting against the heat produced by racks of equipment, the VAX computers and other mini-computers generating substantial heat, the room being kept artificially cool to prevent thermal issues, the temperature being slightly uncomfortable for humans but necessary for machines. The terminal in front of you shows lines of hexadecimal numbers, raw packet data being examined by diagnostic software, the IP headers being visible as structured data, version number, header length, type of service, total length, identification flags, fragment offset, time to live, protocol, header checksum, source address, destination address, options if any. The formalization of these fields, the exact bit positions and meanings, being the subject of endless discussion, the RFC documents, request for comments, being circulated among researchers, proposals being debated, refined, implemented, tested. The source and destination addresses are 32-bit numbers, eventually to be written in dotted decimal notation like 128.3.2.1.00.45, each of the four numbers being an 8-bit byte, the addressing scheme being designed to support hierarchical routing, the early bits identifying networks, the later bits identifying hosts within networks, the structure enabling efficient routing tables, routers only needing to know how to reach networks rather than individual hosts. You type commands to send test packets, watching as they traverse the experimental internet, hopping through multiple networks, packet radio to ARPANET to satellite link to ARPANET again. The routing being dynamic, adapting to network conditions, the traceroute command, not yet invented but conceptually possible, showing the path packets take. The series of hops from source to destination, each router forwarding based on destination address, consulting routing tables built through routing protocols that share information about network topology. The work is painstaking, debugging protocol implementations, finding edge cases where implementations diverge from specifications, discovering that real networks behave differently from theoretical models, packet loss being more common than expected, reordering being more frequent, the need for robustness being continually demonstrated by actual network behavior. Years accumulate. The development continues through the late 1970s and into the early 1980s, TCP and IP being refined, separated into distinct layers. Originally they were a single protocol, TCP/IP, being split into TCP and IP to allow different transport protocols above IP. Implementations being written for different operating systems, the protocols being tested on the growing experimental internet. January 1st, 1983 becomes what network engineers call Flag Day, the day when ARPANET officially switches from NCP to TCP/IP, when the old network control protocol is retired and the new Internet Protocol becomes mandatory, all connected hosts being required to upgrade, the transition being coordinated months in advance, with countdown warnings, with testing periods, with preparation being emphasised because there's no going back, no migration period, just a hard cutover when the old protocol stops working and the new one must function correctly. The night before Flag Day, imagine you're a system administrator, staying late to ensure your machines are ready, checking that TCP/IP implementations are correctly configured, that routing tables are accurate, that applications have been updated to use the new protocol stack. The computer room is quiet, the normal daytime activity absent, just you and the humming machines, the blinking lights, the slight anxiety about whether the transition will work smoothly or whether problems will emerge. At midnight, the switch happens. NCP stops being supported. TCP/IP becomes the only protocol. The network continues functioning, packets continuing to flow, routes being established, connections being made, the transition being surprisingly smooth, the months of preparation having paid off, the careful planning and testing having identified most problems before they became critical. The significance of this moment, Flag Day 1983, is difficult to overstate. TCP/IP becomes the Internet's foundation, the universal protocol enabling different networks to interconnect, the common language allowing diverse systems to communicate. Though networks still debate whether the end-to-end principle embedded in TCP/IP, the idea that intelligence should be at the edges rather than in the network core, was visionary architecture or created the security vulnerabilities that plague the modern Internet, the choice having both enabled Internet's explosive growth and created lasting challenges. Remember those researchers mailing punch cards and waiting weeks for responses? Now they're sending electronic files in seconds, though network speeds in the early 1980s are still measured in kilobits. The patience required for large transfers being substantial, overnight transfers of multi-megabyte files being common, the network being faster than mail but still slow by later standards. Electronic mail emerges as the killer application, the reason people want network access beyond file. Transfers and remote computing, the feature driving adoption beyond the original research community that created the network. Ray Tomlinson, working at BBN on ARPANET development, created email in 1971 as almost an afterthought, a side project while working on other networking tasks. He chose the @ symbol to separate usernames from host names, creating the user at host format that will become universal, recognizable worldwide. The @ sign being available on the keyboard at his workstation, being unused in file names or usernames, being a reasonable visual separator, a symbol that says @ which fits the meaning perfectly. This user at this host. Tomlinson later admitted the choice was somewhat arbitrary, simply selecting something available that seemed to work, not foreseeing that this symbol would become so fundamental to digital communication that email addresses would be as essential as phone numbers, that the @ sign would appear on billions of business cards, that generations would grow up never knowing a time before email addresses were normal parts of identity. The first email message Tomlinson sent was something unmemorable. He later couldn't recall exactly what it said, probably something like QWERTYUIOP, or a test phrase, the historic significance not being recognized at the moment. This being just another test of network functionality, another feature being debugged, another protocol being verified, the revolutionary implications being invisible at the time, hidden in the mundane work of systems programming. You find yourself using email in the early 1980s, your access being through a VAX computer at your university or research lab, logging in through a terminal connected by serial cable, the screen being monochrome, white or green text on black background, the characters being blocky. Bitmap fonts rendered on CRT displays that emit a very faint high-pitched whine from the electron beam. Scanning, a sound that those who worked with such displays remember clearly, but which became rare after flat panels replaced CRTs. The email interface is command line, no graphical elements existing yet, just text, prompts and responses, the interaction being entirely keyboard driven, every action requiring typing a command. You type mail to check for new messages, the program responding with a list of received mail, each line showing sender, date, subject line, the list scrolling past on the screen if you have many messages, the display being sequential, nothing like the random access feel of modern email clients where you can click any message. Reading a message means typing its number, the text appearing on screen, scrolling upward, pausing at the end of each screenful if the message is longer than your terminal height, waiting for you to press space to continue, the pacing being enforced by the technology, speed, reading being impossible when text appears at terminal refresh rates, when you must wait for each page to display before seeing the next, the enforced patience being very different from modern information consumption. Composing email happens in phases. First, addressing. The mail program prompts to, you type the recipient address, user at host.domain. Then subject. You type a brief description, then the body, which might use an editor like Vi or Emacs, or might be entered line by line directly, each line being final once entered. Editing being line-based rather than character-based in simpler mail programs, mistakes requiring retyping. Entire lines, the composition being slower, more deliberate, more considered than the rapid-fire typing of modern email. The arrival of email being indicated by a simple message when logging in. You have mail. The thrill of seeing that notification never quite wears off, even when email becomes daily routine. The possibility that someone has sent you a message, that communication has happened, remains slightly exciting. The asynchronous nature meaning messages arrive at unexpected times, the surprise being part of the medium's character. The protocol for email is SMTP, Simple Mail Transfer Protocol, defining how mail servers exchange messages, how they queue messages for delivery, retry when recipients are unreachable, handle bounces and errors, the standardization allowing different mail systems to interoperate, messages composed on one system being deliverable to any other system, the universal connectivity being transformative. File transfer becomes routine through FTP, the file transfer protocol standardizing how files move between systems, how directories are navigated remotely, how binary and text files are distinguished, the protocol being one of the oldest still in active use decades later, though increasingly replaced by more secure alternatives, the basic model of client-server file transfer remaining unchanged. Using FTP in the 1980s involves a command line client typing FTP hostname to connect, being prompted for username and password, then navigating the remote file system with CD commands, listing contents with ls, downloading with get, uploading with put, the sequence being manual, each file requiring individual commands, batch operations being possible but requiring scripting, the interface being functional but requiring knowledge, not intuitive for novices. The distinction between ASCII and binary transfer modes is critical, often the source of corruption when wrong mode is used. ASCII mode, converting line endings between Unix, LF, Mac, CR, and DOS, CRLF conventions. Binary mode transferring bytes unchanged, using binary mode for text files, potentially mangling line endings, using ASCII mode for programs or images, definitely corrupting them, the mode choice being something every FTP user must learn, usually through the painful experience of transferred files being unusable until correct mode is applied. Anonymous FTP becomes important for software distribution, archive sites allowing public access with username anonymous and any email address as password, the convention being widely adopted. FTP sites hosting GNU software, Linux distributions, RFC documents, scientific data, the distributed archive network being how open source software spreads before web-based distribution, the ftp.* hostnames becoming familiar landmarks of the early internet, ftp.gnu.org and ftp.kernel.org, and mirrors worldwide hosting identical content, the replication being manual, site administrators running scripts to mirror popular archives, the bandwidth costs being shared across many sites. Telnet enables remote login, the protocol being simple, effectively a network transparent terminal session, your keystrokes being sent to the remote system, its output being displayed on your screen, the connection feeling direct despite potentially crossing continents, latency being the main reminder of distance, the characters appearing slightly delayed on slow links, the echo lag being noticeable when typing over satellite links where round-trip time is a quarter second, the pause being disconcerting, making fast typing difficult, requiring adjustment of rhythm to match network speed. System administration becomes distributed through Telnet, no longer requiring physical presence at the machine room, logging in remotely to perform maintenance, edit configuration files, restart services, monitor logs. The convenience being profound, eliminating the need to be physically near the machines you manage, enabling 24/7 operations without requiring staff sleeping in server rooms. The remote access being transformational for how systems are operated, the ability to fix problems from home at 2 a.m. being both blessing and curse, being freed from location but also never being fully off duty. Usenet emerges as distributed discussion system, a network of networks sharing messages organized into newsgroups, hierarchical topics like comp.sys.ibm.pc or rec.arts.sf.written. Users posting messages that propagate to all participating servers, flooding algorithms, ensuring every site eventually receives every message. The distributed nature making censorship difficult, but also making moderation challenging, flame wars becoming common, the first spam message being posted in 1978, an advertisement for a DEC computer demo, hundreds of ARPANET users receiving unsolicited commercial email, the reaction being immediate and negative, the term spam not yet being used, but the phenomenon being recognized as problem. The early internet culture develops its own norms and expectations, netiquette being the informal rules governing behavior, things like not typing in all caps, considered shouting, trimming quoted material in replies, avoiding excessive cross-posting across news groups, the social conventions being transmitted through FAQs and through criticism of violators, self-governance being the primary mechanism of maintaining civil discourse. Years continue passing. You now stand in a computer center in the mid-1980s watching the domain name system being deployed, solving a problem that has become increasingly acute as the network grows, remembering and typing numeric IP addresses. In the early internet, connecting to a remote computer means knowing its IP address, typing something like telnet 128.3.2.1.0.0.45 to connect to a specific machine at UC Berkeley. But remembering numbers is difficult, especially as the number of hosts grows from hundreds to thousands to tens of thousands. The original solution was a hosts file, literally a text file named hosts.txt, maintained at Stanford Research Institute, listing all known hosts with their addresses and names, administrators periodically downloading the updated file, the manual process breaking down as the network scaled. Paul Mockapitris, working at USC Information Sciences Institute in 1983, designed the domain name system after considering various proposals for scaling naming beyond the failing hosts.txt file approach. His design created a hierarchical distributed database that translates human-friendly names into IP addresses. The hierarchy allowing delegation of authority, no single organization needing to maintain all names. The distribution enabling high performance through caching and resilience through replication. The elegance of the design being that it scales from dozens to billions of names without fundamental changes, the architecture being sound enough that it remains largely unchanged 40 years later. The DNS hierarchy starts conceptually at the root, represented by a dot that's usually invisible in everyday use, beneath which are top-level domains. Generic TLDs, like .com for commercial, .edu for educational institutions, .gov for US government, .mil for military, .org for organizations, and country code TLDs like .uk for United Kingdom, .fr for France, .jp for Japan, each country having its own policies for registration. Each top-level domain can delegate subdomains, stanford.edu being a subdomain of .edu, www.stanford.edu being a subdomain of stanford.edu, mail.cs.stanford.edu being a further subdomain, the tree structure allowing arbitrary depth, the delegation enabling decentralized management, no central authority needing to know about every machine at every institution. Imagine you're a system administrator in 1986, configuring one of the early DNS servers for your university, your responsibility being to translate your local host names into IP addresses for the rest of the Internet, running bind Berkeley Internet Name Domain software, the reference implementation that will dominate DNS serving for decades, on a Sun workstation, the pizza box-shaped Sun 3 model perhaps, distinctive orange Sun Microsystems logo on the front, the machine running Sun OS Unix variant. The server room where you work is cool, maintained at perhaps 65 degrees Fahrenheit. Uncomfortable for humans but necessary for the electronics, the air conditioning labouring constantly against the heat produced by racks of equipment, each machine being a heat source, collectively warming the room despite the cooling efforts. The smell is of electronics and cold metal and the ozone produced by monitors and high-voltage equipment, the distinctive scent of computer rooms that those who worked in them remember clearly. You edit zone files using VI or Emacs on the Sun workstation, the zone file being a text file, structured data but human-readable, each line being a resource record specifying some aspect of your domain's DNS information. An A record maps a host name to an IPv4 address, www in A17.1.6.4.1.5.123, meaning www.yourdomain.edu is at that address. An MX record specifies mail exchange servers where email for your domain should be delivered. NS records delegate subdomains to other name servers, allowing departments to manage their own portions of the namespace. CNAME records create aliases allowing one name to point to another, useful for creating convenient shortcuts. The syntax is particular, sensitive to whitespace, requiring specific formats. errors in zone files causing the entire zone to fail loading, the name server logging cryptic error messages that must be deciphered, the debugging process being tedious, checking each record for typos, verifying that names end with dots when they should be absolute rather than relative to the zone origin, confirming that serial numbers increment when changes are made, so secondary servers know to transfer updated zones, the attention to detail being necessary for correct operation. After editing zone files, you must reload the name server, sending it a HUP signal to reread configuration, watching the logs to confirm successful loading, testing resolution with ernst lookup or dig commands, verifying that queries return expected answers, checking that changes have taken effect, the verification being manual, requiring human attention. No automated testing infrastructure existing in these early days. Reliability depending on careful administration. The Resolver library provides the client-side DNS functionality, the code that applications use when they need to translate names to addresses, the getHostByName function being the standard interface in C programs, called whenever a program connects to a named host, the library querying configured DNS servers, handling the recursion if necessary, querying root servers if no cached information exists, following referrals through the hierarchy, caching results according to their TTL values, the entire process being invisible to applications, which simply call the function and receive back an IP address, the complexity being abstracted away, hidden behind a simple interface. The root servers are critical infrastructure, the foundation of the entire DNS hierarchy, currently 13 named servers labelled A through M, though actually many more physical machines using Anycast routing, so that a.root-servers .net resolves to different servers depending on your location, the redundancy being essential for resilience, the global distribution reducing latency, the importance being so great that root servers are operated by different organizations worldwide to prevent single points of failure. The root servers don't know the address of every domain, they know the addresses of TLD servers, delegating responsibility for each TLD, a root query for www.stanford.edu, returning referral to .edu name servers, which then refer to stanford.edu name servers, which provide the final answer, the chain of delegation being followed automatically by recursive resolvers, the end user never seeing the multiple queries happening behind the scenes. The propagation of DNS changes takes time, an inherent characteristic of distributed caching systems, updates to zone files needing to be loaded by primary name servers, secondary name servers periodically checking primary servers for updates through zone transfers, caches at recursive resolvers gradually expiring old information based on TTL values, the full global propagation potentially taking hours or days, the eventual consistency being acceptable trade-off for the system's scalability and availability, the tolerance for temporary inconsistency being built into the protocol design, acknowledging that perfect immediate consistency across a global distributed system is impossible. The time to live value in each DNS record specifies how long it can be cached, the administrator choosing values balancing between reducing query load, long TTLs mean fewer queries, and enabling rapid changes, short TTLs mean changes propagate faster. Typical values ranging from minutes to days, depending on how frequently records change, the trade-off being fundamental to distributed systems, consistency versus performance being eternal tension. Remember manually typing IP addresses when connecting to remote hosts. Remember maintaining hosts.txt files that quickly became obsolete. Now typing ftp.stanford.edu automatically finds the correct server, the name being resolved to address transparently. The DNS system having become invisible infrastructure, working so reliably that people notice only when it fails, DNS problems becoming a catch-all explanation for network issues, the system's importance being greatest when it's absent, when names stop resolving and the internet seems broken. The story continues, the internet growing, evolving, being commercialized, becoming accessible to ordinary people beyond the research community that created it. But rest comes easier knowing that the foundations are in place, that the protocols enabling modern connectivity were designed by people typing on teletypes, configuring VAX machines, running network cables between buildings, the patient work of engineers solving problems one protocol at a time, one network connection after another, building the infrastructure that now carries these words to your eyes. The invisible network spanning the globe, connecting billions of devices, all based on those early decisions, those first connections, those fundamental protocols designed when the internet was for computers and a dream of resilient networking. Decades have passed since those early ARPANET connections, since the patient work of establishing TCP/IP, since DNS made names friendlier than numbers. You now find yourself at CERN, the European Organisation for Nuclear Research, in Switzerland in March of 1989, sitting in an office where one of history's most influential documents is being written, though its significance won't be recognised for months, perhaps years, the revolutionary implications being hidden in a modest proposal about information management. Tim Berners-Lee, a British computer scientist working at CERN, is typing a document titled Information Management, a Proposal, describing a system for organising and accessing the vast amount of documentation, research papers and technical specifications scattered across CERN's computing systems. The problem he's addressing is one of information overload, researchers unable to find documents they need, knowledge being trapped in isolated systems, the growing complexity of collaborative physics research requiring better tools for sharing and discovering information. His proposal describes a web of linked documents, hypertext allowing readers to jump from one document to related ones by clicking on links, the concept being not entirely new, Ted Nelson and others having imagined hypertext systems for decades. But Berners-Lee's innovation is making it work across the internet, making it distributed rather than centralized, making it simple enough that anyone can create and publish documents without requiring permission or centralized coordination. The proposal is submitted to Berners-Lee's supervisor, Mike Sendall, who writes on the cover vague but exciting and gives permission to pursue it as a side project, the lukewarm endorsement being sufficient, the modest beginning being typical of technologies that will reshape the world, often starting as experiments, side projects, solutions to immediate practical problems rather than grand visions of transformation. Over the following years, Berners-Lee implements his vision, creating the three fundamental technologies that define the World Wide Web: HTML, hypertext markup language, for structuring documents with headings, paragraphs, lists, and links; HTTP, hypertext transfer protocol, for transferring these documents across networks; and URLs, uniform resource locators, for addressing documents, specifying their location on the web in a standardized format that anyone could use. Imagine you're watching Berners-Lee work in 1990, his office at CERN cluttered with papers and technical manuals, a Next computer on his desk, Steve Jobs' elegant black cube workstation being the development platform, the Next Step operating system providing sophisticated development tools, the machine being expensive and rare but available at CERN through Jobs' educational initiatives, the choice being fortunate because Next's tools accelerate development significantly, the object-oriented programming environment making it easier to create the first web software. The first web server runs on this Next machine, serving pages written in HTML, simple documents with text and links, no images initially, no complex layouts, just structured text with the ability to reference other documents through hyperlinks. The first web browser, also running on the Next, is both a viewer and an editor, allowing not just reading documents but creating and modifying them, the vision being bidirectional, everyone being both consumer and publisher, though this write capability will largely be lost as the web commercializes, becoming primarily a read-only medium for most users until social media resurrects user-generated content decades later. The first website's URL is info.cern.ch, going live on August 6, 1991, the page explaining what the World Wide Web is, how to create web pages, how to set up a server, the meta quality of the first website being appropriate, the web explaining itself, documentation being its first use case, the page containing the essential information needed for others to join this new web, the instructions being clear, the barrier to entry being deliberately low. The address still works today, redirecting to a historical recreation, the longevity being remarkable, URLs from 1991 still being resolvable, the commitment to backward compatibility being part of the web's design philosophy. In April 1993, CERN makes a crucial decision, releasing the World Wide Web's code into the public domain, declaring that anyone can use it freely, no fees, no licenses, no restrictions. The decision enabling explosive growth, removing barriers to adoption, ensuring the web remains open rather than becoming proprietary technology controlled by one organization. Whether commercialization ultimately enhanced or degraded the academic collaborative spirit that created the web remains debated among historians and technologists. The tension between openness and profit becoming permanent feature of internet culture. The original vision of free information exchange competing with commercial interests. The balance shifting over time, the question having no simple answer, the debate continuing today. The web grows slowly at first, technical users at universities and research labs being early adopters, manually creating HTML files, setting up servers, experimenting with hyperlinks, the community being small, enthusiastic, collaborative, but the release of Mosaic browser in 1993 transforms accessibility dramatically, making the web available to non-technical users for the first time. Developed at the National Center for Supercomputing Applications at the University of Illinois by Mark Andreessen and Eric Beiner. Mosaic is the first browser to display images in line with text, making the web visual rather than purely textual, the graphical nature being compelling, the ease of use being revolutionary compared to command-line internet tools. You find yourself installing Mosaic on a Unix workstation in late 1993, downloading the source code via FTP, compiling it according to the installation instructions, the build process taking time, the computer working through compilation, generating executables, the wait being part of the experience, nothing being instant. When you finally launch Mosaic, the window opens showing a default page and you type a URL into the location bar, pressing enter, watching the status bar at the bottom showing connecting, then transferring data. Then suddenly a page appears, text and images together, blue underlined links that you can click to jump to related pages. The experience being intuitive, requiring no manual, no training, just obvious interaction. The design being so natural that it seems inevitable in retrospect, though countless hours of thought and iteration produced this simplicity. The first page you visit might be the NCSA Mosaic homepage, or perhaps the What's New page that lists recently created websites, the list being short enough to be manageable, dozens or hundreds of sites rather than millions, small enough that individuals could browse comprehensively, exploring the entire web being possible in hours or days, the intimacy of the early web being lost as it scales, the personal handcrafted pages giving way to professional corporate sites and eventually to algorithm-driven platforms. The web's growth accelerates dramatically through the mid-1990s, Netscape Navigator being released in 1994 as a commercial successor to Mosaic, Mark Andreessen having left NCSA to co-found Netscape Communications Corporation, the browser becoming dominant, Netscape compatible being a quality that website developers target, the browser wars beginning, Microsoft entering with Internet Explorer bundled with Windows, the competition driving rapid feature addition but also fragmentation, different browsers supporting different features, websites displaying best viewed in Netscape or optimized for Internet Explorer, badges, the lack of standards compliance being frustrating for developers trying to create cross-browser compatible sites, the ecosystem being chaotic, creativity and competition being intermingled with incompatibility and frustration. Businesses begin creating websites, the .com domain explosion happening, companies rushing to establish web presence, www.companyname.com. Becoming standard business infrastructure alongside phone numbers and addresses, the web transitioning from academic research network to commercial platform. The gold rush atmosphere of the late 1990s driving investment, speculation, eventually the .com bubble that will burst in 2000. But through the mid-90s the optimism is unbounded. Every company needing a website, web developers being in demand, HTML being learned by hundreds of thousands, the barrier to entry being low, view source showing any pages HTML, learning by example being common, the open nature of the web enabling rapid skill diffusion. The aesthetic of 1990s websites is distinctive, memorable to those who experienced it, the limitations of the technology being visible in design choices, the constraints shaping creativity. Under construction, animated GIFs indicating incomplete sections, the worker with a shovel or construction barriers being ubiquitous, the admission of incompleteness being accepted, background MIDI, music auto-playing when pages load, the synthesized melodies being tinny but enthusiastic, the automatic audio being startling, often unwanted, the volume control being quickly sought. Blinking text elements, the tag being supported by Netscape, overused by enthusiastic developers, eventually becoming despised, disabled by default in later browsers, the blinking being attention-grabbing initially, but quickly irritating. Tiled background images making text difficult to read, the pattern repeating across the page, the aesthetic choice overwhelming content. Visitor counters showing how many people have visited, the incrementing numbers being source of pride, validation of site popularity. Web rings, linking sites with similar topics, navigation bars with previous and next buttons allowing browsing through curated collections, the distributed nature being appealing, the communities forming around shared interests. Guest books where visitors leave comments, predating modern comment systems, the social aspect being manual, hosts moderating by hand, the interaction being personal, slower, more considered than later social media. Remember the command line, FTP and Telnet tools from the early internet. Now clicking a link instantly retrieves a page from across the world, the web's ease of use making the internet accessible to non-technical users, driving mainstream adoption, transforming from specialist tool to mass medium, the democratization being profound, the barrier to entry being lowered enough that millions can participate rather than just thousands, the cultural impact following from this accessibility. The dial-up modem becomes the sound of the internet for a generation, the screech and static of modems negotiating connections being iconic, instantly recognizable decades later as the sound of going online. The acoustic modem handshake being physical reminder of the connection process, making abstract networking concrete and audible. You find yourself at home in 1996, sitting at a desk with a gateway or compact computer, beige case, and CRT monitor, the operating system being Windows 95 or perhaps Windows 3.1, the modem being internal or an external box connected by serial cable, the phone line plugged into the modem, the same line used for voice calls, the internet connection and telephone being mutually exclusive, going online meaning the phone is busy, incoming calls going to busy signal, the conflict being accepted trade-off, families negotiating, who gets to use the phone line when. You double-click the internet connection icon, the modem dialing, the phone's DTMF tones as it dials the ISP's number, the familiar sequence of beeps, then the handshake sequence beginning, screeching tones as modems negotiate protocols, testing different modulation schemes, finding highest common speed, the acoustic coupling being literal, the sound being the communication, the handshake establishing data rate and compression, the connection settling at 28.8 kilobits per second. If you're lucky, perhaps 14.4 kilobits per second if the line quality is poor, the speed being dramatically faster than the 300 baud modems of early ARPANET, but still slow by later standards, though 56K modems seemed revolutionary when they appeared in 1997. A speed modern mobile data finds charmingly nostalgic, a 4G phone connection being hundreds of times faster than the best dial-up modem, the patience required for dial-up being difficult to convey to those who've never experienced it. The connection established, a dialog box appears showing connection speed, bytes transferred, connection duration, the statistics being monitored, watching the numbers increment being oddly satisfying. You open Netscape Navigator, the browser loading, displaying your chosen homepage, probably Netscape's start page or perhaps Yahoo, the popular early portal and search directory. The hand-curated categories being how people found sites before search engines became sophisticated. Clicking a link begins the loading process, the status bar showing progress, the page loading progressively. Text appearing first, then images loading one by one, the placeholders showing the image dimensions, the actual images downloading slowly, sometimes taking seconds or minutes for large images, the compression artifacts of JPEG being visible, the dithering of GIF images being obvious, the 256 colour palette being limiting, the low-resolution web graphics being accepted, necessity-given bandwidth constraints, the patience required for web browsing over dial-up being substantial, clicking a link meaning commitment, waiting for the page to load, the hourglass cursor spinning, the uncertainty about whether the page is loading or the connection has stalled, the refresh button being pressed hopefully, sometimes making things worse by restarting the download, the frustration being common but accepted, the speed being slow but still miraculous compared to no internet access at all. The generation experiencing dial-up understanding both its limitations and its transformative nature, the modern expectation of instant loading being foreign concept, waiting being normal, time being measured in minutes rather than milliseconds, the psychological adaptation to delay being necessary, the habit of opening multiple links in separate windows and then reading them as they load being common strategy. the workarounds being creative responses to technical constraints. While web browsing happens over these fragile dial-up links, the physical infrastructure supporting the internet is being massively expanded, the backbone networks being upgraded, fibre optic cables being laid across continents and oceans, the invisible infrastructure enabling the visible applications, the investment in physical layer being essential for the internet's growth, billions being spent on cables and equipment that users never see but completely depend on. You find yourself aboard a cable-laying ship in the North Atlantic in 1988, watching the deployment of TAT-8, the first transatlantic fibre optic cable, replacing older copper coaxial cables with fibre strands carrying light pulses. The bandwidth increase being enormous from megabits to gigabits, the capacity growth enabling the internet's international expansion. The ship moves slowly, deliberately, unspooling cable from huge drums in the hold, the cable descending to the ocean floor kilometres below, the rate being roughly 10 kilometres per day, the Atlantic crossing taking weeks, the pace being measured, the precision being necessary, the cable route being carefully surveyed, avoiding rough terrain, unstable slopes, fishing grounds where trawlers might damage cables, the planning being extensive, years of preparation for the actual laying. The cable itself is surprisingly thin, considering its importance, perhaps the diameter of a garden hose, the core being hair-thin optical fibres carrying the light signals, surrounded by protective layers. Copper for power, steel wire for strength, multiple sheaths of waterproofing, the construction being complex despite modest external dimensions, each layer serving specific purposes. The engineering being sophisticated, designed for decades of operation on the ocean floor without maintenance. The reliability being essential because repairs are difficult, expensive, require weeks of ship time. Every 50 to 60 kilometres, repeaters are spliced into the cable, amplifying the optical signals, maintaining signal strength across the ocean. The repeaters being powered by electrical current sent down the cable from shore stations. The engineering being remarkable, devices designed to operate continuously for 25 years or more without service, sealed units rated for deep sea pressure. The reliability requirement being absolute because accessing repeaters on the ocean floor is nearly impossible. The investment in quality being justified by the cost of failure. The shore stations where cables land are massive facilities, unassuming buildings on remote coastlines, inside being racks of optical amplification equipment, electrical systems generating power for repeaters, monitoring gear tracking cable health, backup generators ensuring continuity, the facilities being critical infrastructure, protected, monitored continuously, the staff being small but skilled, the operations being largely automated, alarms summoning engineers only when problems arise. Data centers are where the internet becomes tangible, where abstract protocols run on physical machines, where the ethereal network materializes in racks of servers consuming kilowatts, generating heat, requiring cooling, occupying real estate, employing technicians, the cloud having very solid foundations, the virtua being implemented on physical. Imagine walking through a data center in 2005 being escorted by a facilities engineer, the experience being sensory, overwhelming, industrial despite housing digital infrastructure. You enter through security checkpoints, badge readers controlling access, cameras monitoring entrances, the security being necessary for protecting both infrastructure and customer data. Authorized personnel only beyond this point. The restricted areas being most of the building, only lobbies and customer tour areas being freely accessible, the operational spaces being tightly controlled. The noise is the first assault on your senses as doors open to the server floor. A constant loud hum from thousands of cooling fans, every server having multiple fans, typically 3 to 6 per unit, each spinning at thousands of RPM, moving air through heat sinks cooling CPUs and memory, collectively producing sound measured at 80 to 90 decibels, requiring hearing protection for extended stays, conversation being difficult, shouting being necessary to be heard, the acoustic environment being hostile to humans, optimized for machines rather than people, designed for efficiency, not comfort, the experience being physically overwhelming, the visceral reminder that data centers are industrial facilities despite housing digital infrastructure. The air is noticeably cool, maintained at 65 to 70 degrees Fahrenheit, the temperature being optimal for equipment reliability, slightly uncomfortable for humans, especially after physical work, the cold aisles being where cool air enters servers, hot aisles being where exhaust emerges. The temperature difference being 15 to 20 degrees, standing in a hot aisle being surprisingly warm despite overall room being cold, the air handling being organised into contained systems, physical barriers separating hot and cold, preventing mixing that would reduce efficiency, the airflow being designed with computational fluid dynamics, every aspect optimised for cooling performance, the engineering being sophisticated, the investment being justified by energy savings over decades. The rows of server racks extend into the distance, perspective making far rows seem to converge, black cabinets with glass or metal doors, inside being layers of servers, each one U or 2 U high, 1 or 2 rack units, the density being remarkable. 42 U racks holding dozens of individual servers, each rack being multiple kilowatts of power consumption and heat generation. Modern racks sometimes exceeding 20 kilowatts. The concentration being intense, the power distribution being critical infrastructure, redundant power feeds ensuring that no single failure can down a rack, dual power supplies in each server drawing from separate circuits, the redundancy being layered at component, system and facility level. The raised floor beneath your feet is distinctive, perforated tiles covering a plenum, the space beneath being used for cold air distribution, computer room air conditioners pushing cold air under the floor, rising through perforations in cold aisles, the raised floor being typically 18 to 36 inches high. Enough space for substantial airflow, cables also running beneath floor. In some designs, though overhead, cable trays are increasingly common, the separation of power and data being important, electromagnetic interference being concern. The cabling is extensive and meticulously organised. Fibre optic cables connecting switches to servers, Ethernet cables linking equipment, power cables running from distribution units to server inlets, the cables being bundled with Velcro straps labelled with identification, zip-tied to maintain organisation, cable management being serious business, messy cabling making troubleshooting difficult, finding the right cable among thousands being challenging without organisation, the discipline of proper management being essential for operational efficiency, the person who doesn't organise cables properly being the person who struggles to debug problems at 3 a.m. The consequences of poor practices being immediate and frustrating. The lights blink constantly on equipment, status LEDs on servers and network switches, green typically indicating normal operation, amber or red indicating problems. The pattern of blinking lights being information-rich to trained eyes, solid illumination versus rapid blinking versus slow blinking, all conveying different states. The frequency of flashing indicating network activity levels. The visual language of data center equipment being learned through experience. The ability to glance at a rack and assess health being valuable skill. Pattern recognition being how experienced engineers quickly identify issues. Routing protocols become increasingly sophisticated as the internet scales, the simple routing of early ARPANET, being insufficient for thousands of interconnected networks, each needing to find paths to destinations while respecting policy constraints, economic relationships, performance requirements. Border Gateway Protocol, BGP, becomes the standard for interdomain routing, enabling autonomous systems to exchange routing information, each AS controlling routing policies, making business decisions about which routes to announce and accept. BGP, enabling the policy-based routing that makes commercial internet possible, allowing ISPs to implement business relationships through routing policies, the technical protocol enabling economic models. A BGP session between routers in different autonomous systems establishes slowly, deliberately, the protocol being designed for stability rather than speed. First, a TCP connection is opened on port 179, the three-way handshake completing the reliable transport being necessary for routing protocol traffic, lost routing updates being unacceptable. Then BGP messages are exchanged, the open message containing AS number, BGP version, hold time, the parameters being negotiated, both sides agreeing on capabilities. The full routing table is transferred, potentially hundreds of thousands of routes, each route being a destination network prefix, AS path showing which network's traffic traverses, attributes indicating preferences and policies. The initial transfer taking minutes or longer for large tables, the bandwidth and processing time being substantial, but this overhead being incurred only once per session, subsequent updates being incremental, sending only changes. Once established, BGP sessions remain stable for weeks, months, years, if everything works correctly, the persistence being design goal, flapping sessions causing routing instability, rapid route changes causing convergence problems, the protocol preferring to maintain stable but slightly suboptimal routes over constantly changing optimal routes. The trade-off being deliberate, stability being more valuable than perfection in infrastructure protocols. Network operations centers are where this complexity is monitored and managed, where humans oversee the automated systems, where problems are detected and resolved, where the Internet's reliability is maintained through constant vigilance. Imagine visiting a NOC in the early 2000s, being shown around by a senior network engineer, the environment being distinctive, purpose-built for 24/7 monitoring and response. The room is dominated by large displays on the front wall, multiple screens showing different views of network status, one displaying a geographical map with network topology overlaid, lines showing connections between cities, colours indicating link utilization, green for normal, yellow for elevated traffic, red for congestion, the visual representation allowing quick assessment of network health, anomalies standing out, the geographic context being important, knowing where problems are located enabling appropriate response. Another screen shows traffic graphs, bandwidth utilization over time for major links, the patterns being distinctive, diurnal cycles visible, traffic low during night, rising in morning as business opens, peaking in afternoon and evening as residential usage increases, declining overnight as users sleep, the regularity being expected, deviations being investigated, unusual patterns indicating potential problems, distributed denial of service attacks showing as sudden traffic spikes, equipment failures showing as sudden drops, the pattern recognition being key skill for NOC operators. A third screen shows alarm summary, equipment sending SNMP traps when problems are detected, link failures, high CPU usage, memory exhaustion, temperature alarms, the alerts being prioritized by severity, critical alarms requiring immediate attention, warning alarms being monitored, informational messages being logged, the filtering being necessary, avoiding alert fatigue. Too many low-priority alarms causing important ones to be missed. The threshold tuning being ongoing process, balancing between catching problems early and avoiding false alarms. The NOC is staffed around the clock, engineers working 8 or 12-hour shifts, coverage being continuous, the night shifts being quiet usually, giving opportunity to catch up on documentation, training, project work, but becoming intense when problems occur. The contrast being stark, hours of routine monitoring, interrupted by minutes of frantic troubleshooting, the adrenaline being real, major outages affecting thousands or millions of users, creating pressure, the responsibility being heavy, knowing that people depend on connectivity for business, communication, emergency services. The weight of that responsibility being motivating, the satisfaction of successful problem resolution being significant. The tools used in NOCs have evolved over years. Early NOCs using command line tools and simple scripts. Modern NOCs having sophisticated graphical dashboards, but the fundamentals remaining constant, monitoring for anomalies, investigating problems, coordinating responses, communicating with affected parties. The coffee consumption is legendary, pots brewing constantly, the caffeine being necessary for night shift alertness, the coffee quality usually being terrible, but the quantity being unlimited, the burned taste of coffee that's been on the hot plate too long being familiar to all NOC veterans. The culture of NOCs is distinct, the shared experience of solving problems under pressure creating bonds, the war stories of memorable outages being told and retold, each engineer having stories of the time when everything broke simultaneously, when multiple Tier 1 providers had routing problems, when major submarine cables were cut by fishing trawlers, when DDoS attacks overwhelmed defences, the stories being both educational and entertaining, lessons learned being transmitted through narrative, the informal knowledge transfer being as important as formal training. You observe a traceroute command revealing packet journeys, typing traceroute www.example.com from a terminal, watching output scroll, each line representing one hop along the path, the router's IP address and often host name. The round-trip time measured 3 times per hop showing variation, the consistency or variance being informative, stable latencies indicating healthy links, variable latencies suggesting congestion or routing instability, lost probes showing packet loss, asterisks appearing where routers don't respond to traceroute probes, some network administrators configuring routers to not respond to limit information disclosure, the incomplete traces being common, interpreting partial results being necessary skill. The path revealed might traverse 15 or 20 hops, starting from your local network, hopping to your ISP's aggregation router, then to regional backbone, national Tier 1 provider, international submarine cable, landing in another continent, traversing another Tier 1 network, descending through destination ISP's network hierarchy, finally reaching destination server. Each hop being deliberate choice made by routing protocols. The path optimization considering factors beyond simple hop count, taking into account AES path length, local preferences, multi-exit discriminators, community tags. The BGP attributes influencing routing decisions in complex ways, the visible route being result of countless invisible policy decisions. Remember ARPANET's 4 nodes connected by 50 kilobit links. Now BGP routes packets through over 90,000 autonomous systems worldwide, the scaling being remarkable, the exponential growth being sustained for decades, the protocols designed when networks numbered in dozens, now handling networks numbering in tens of thousands. The architecture being fundamentally sound, proven through scale, though approaching certain limits. IPv4 address exhaustion having already occurred, requiring IPv6 deployment, routing table growth continuing, approaching router memory limits, the system being robust but not infinite, the challenges ahead being significant but manageable through continued engineering innovation. Broadband internet transforms the user experience in the early 2000s. The shift from dial-up being dramatic, life-changing for those who experienced it. The always-on nature being fundamentally different, no more connecting and disconnecting rituals, no more modem screeches, no more busy phone lines preventing incoming calls. The internet becoming ambient, always available, changing how it's used, enabling new applications, requiring persistent connectivity. Instant messaging conversations continuing for hours, online gaming becoming practical, streaming media becoming possible, all depending on continuous fast connection that dial-up couldn't provide. DSL brings broadband over existing phone lines, using frequencies above voice range, filters separating voice and data, allowing simultaneous use, the convenience being substantial, no more choosing between internet and phone, asymmetric speeds, matching usage patterns, downloads being faster than uploads because most users consume more than they produce, typical speeds being 1.5 megabits per second down, 384 kilobits per second up, dramatically faster than dial-up, the experience being transformative, web pages loading in seconds rather than minutes, downloads measuring megabytes, completing in minutes rather than hours, the quantitative improvement producing qualitative change in how internet is used. Cable modems bring broadband over cable TV infrastructure, coaxial cables carrying both television and data, cable companies deploying DOCSIS modems and upgrading infrastructure, speeds being competitive with DSL, sometimes faster, 3 to 10 megabits per second being typical, but bandwidth being shared among neighbours, the cable network being like an Ethernet segment, capacity divided among active users, heavy usage by neighbours potentially affecting your speed, peak evening hours sometimes showing degradation, the contention being invisible, usually but occasionally noticeable. The trade-off being accepted, cable generally faster than DSL, but shared rather than dedicated. Fibre to the home represents ultimate residential connection, optical fibre running all the way to individual houses, speeds measured in hundreds of megabits or gigabits per second, the capacity being enormous, the infrastructure investment being substantial, but the technology being future-proof. Fibre supporting speed increases through endpoint equipment, upgrades without replacing cables. The physics of light through glass fibre allowing decades of growth. The deployment being gradual, starting in dense urban areas, slowly expanding to suburbs, rural areas often waiting years or decades. The digital divide being partially about infrastructure economics, the cost per customer being high in sparsely populated areas, market forces alone being insufficient for universal coverage. Wi-Fi transforms internet access from tethered to mobile within buildings. The freedom being liberating, walking around home or office with laptop, sitting in different rooms, working from the couch or the patio, the wireless connection following you, the convenience being transformative. Wireless access points become common household devices, the early models being standalone boxes with antennas, later versions being integrated into cable modems or DSL gateways. The all-in-one devices simplifying home networking, reducing the box count, the integration being consumer-friendly. The 802.11 standards evolve through generations, each bringing improvements in speed, range, reliability, the backwards compatibility being maintained, newer devices working with older access points, older devices working with newer access points. The graceful degradation being designed into the protocol family from the beginning, the investment protection being important for consumer adoption, people not wanting devices becoming obsolete when infrastructure upgrades. 802.1 1B arrives in 1999, operating in the 2.4 GHz band, providing 11 megabits per second maximum speed, though real-world throughput being lower due to protocol overhead, interference, distance from access point, the actual speeds being perhaps 5 to 6 megabits per second, under good conditions still faster than most dial-up connections, enabling wireless broadband access, the appeal being obvious, the adoption being rapid. 802.11G follows in 2003, still using 2.4 GHz, but with improved modulation, reaching 54 megabits per second, theoretical maximum, perhaps 20 to 25 megabits per second, real throughput. Backwards compatible with 802.11b. The coexistence being important, protecting existing investments while enabling higher speeds. The transition being smooth, gradual, as devices upgrade over years. 802.1 1AN launches in 2009, being first standard to use multiple antennas, MIMO, multiple input, multiple output technology allowing spatial multiplexing, multiple data streams being transmitted simultaneously, the theoretical maximum reaching 600 megabits per second with 4 spatial streams, though typical consumer devices supporting 2 streams for 300 megabits per second. Maximum, real throughput being perhaps 100 to 150 megabits per second under excellent conditions, finally making Wi-Fi suitable for high-definition video streaming, the performance being adequate for demanding applications. 802.11 AC arrives in 2013, moving to 5 GHz band to escape 2.4 GHz congestion, using wider channels and more spatial streams, exceeding gigabit speeds in theory, though real-world performance being lower but still impressive, hundreds of megabits being achievable, the wireless performance exceeding many wired connections, Wi-Fi becoming preferred even when Ethernet is available, the convenience outweighing the minor performance differences. The spectrum becoming increasingly crowded being problem, especially in 2.4 GHz, where Wi-Fi shares space with Bluetooth, microwave ovens, cordless phones, baby monitors, the interference being noticeable in apartment buildings where dozens of access points compete for limited channels. The channel planning being necessary, using Wi-Fi analyzer apps to find least congested channels. The 5 GHz band being cleaner but having shorter range, the radio physics being unforgiving, higher frequencies being absorbed more readily by walls and obstacles, the range/speed trade-off being inherent. Mobile data brings internet to phones wherever cellular towers provide coverage. The cellular networks being repurposed for data, originally designed for voice now carrying ever-increasing data traffic. The shift from voice to data being dramatic, voice minutes declining as messaging and VoIP replace traditional calls. The business model of cellular carriers being transformed, unlimited voice becoming common while data being metered, the economics reversing. 3G networks enable basic mobile web browsing, speeds being measured in hundreds of kilobits, perhaps 1 or 2 megabits, enough for email, basic web pages, low-quality streaming, the experience being usable but limited, the expectations being set by dial-up era, mobile data being acceptable despite being slower than home broadband, the convenience of connectivity anywhere outweighing speed limitations. 4. GLTE revolutionizes mobile internet, speeds rivaling or exceeding home broadband, tens of megabits being typical, hundreds being possible in ideal conditions, high-definition video streaming becoming practical on phones, the mobile. First trend accelerating, many users abandoning home broadband entirely, depending solely on mobile data, the smartphone becoming primary internet device, the desktop becoming secondary or unnecessary. The platform shift being profound, changing how services are designed, how content is consumed, how people interact with internet. 5G promises even higher speeds, millisecond latencies, massive device density, the marketing being ambitious, the reality being gradual deployment, the initial rollout being limited to dense urban areas, the coverage gaps being filled slowly, the transition taking years. As with all previous cellular generations, the coexistence of multiple generations being normal, devices connecting to whatever network is available, falling back gracefully when newer technology is unavailable. Smartphones become primary internet access devices for billions of people, many never owning computers, experiencing internet exclusively through phones. The mobile-only population being significant globally, the assumption of desktop access being false for large portions of world, the design implications being important, mobile-first thinking becoming necessary, responsive design being mandatory, touch interfaces being default, mouse and keyboard being secondary considerations, the entire web being reconsidered through mobile lens. Cloud computing emerges in mid-2000s, Amazon Web Services launching in 2006, offering computing as utility service, virtual servers rentable by the hour, storage purchasable by the gigabyte, the elastic nature, meaning capacity scaling up or down based on demand, capital expenditure becoming operational expenditure, the economics being attractive for startups lacking infrastructure budget, the scalability enabling growth without upfront investment, the model being revolutionary, enabling modern startup ecosystem, companies launching without server rooms, without capital equipment, paying only for resources actually used, the flexibility being transformative, the abstraction being complete, developers never seeing physical machines, interacting through APIs, infrastructure becoming software-defined, programmable. Content delivery networks accelerate content delivery, caching popular content at edge locations near users. Netflix Open Connect placing servers inside ISPs, YouTube caching videos regionally, the result being most streaming traffic stays local, never crossing backbone links. The efficiency being remarkable, the scale being enormous, petabytes being cached and served daily. The global CDN infrastructure being invisible but essential, the reason videos load in seconds, the replication being automatic, the optimization continuous. The story continues, the internet growing, evolving, but rest comes easier knowing the infrastructure works, that protocols handle complexity, that engineering scaled from 4 computers to billions of devices, that somewhere packets flow through cables, cross oceans, route through networks, carrying your data to destinations worldwide, the invisible network functioning quietly, patiently, endlessly. Time moves forward again, the internet continuing to evolve, new applications emerging, the infrastructure being increasingly taken for granted, the network becoming invisible, embedded in daily life so completely that its absence is shocking, its presence being assumed. You now find yourself in the mid-2000s, watching a transformation in how people use the internet, the shift from consuming content created by professionals to creating and sharing content themselves, the read-only web becoming read-write, the audience becoming participants. Facebook launches in 2004, initially limited to Harvard students, Mark Zuckerberg's college project, then expanding to other Ivy League schools, gradually opening to all universities with .edu email addresses, eventually opening to everyone over age 13 in 2006, the social network growing exponentially, the friend connections creating network effects, each new user making the service more valuable for existing users, the growth being viral, organic, driven by word of mouth and genuine utility, people wanting to connect with old friends, share updates about their lives, see what others are doing, the basic human desire for connection being channeled through digital infrastructure. The experience of early Facebook being simpler than what it would become. Profile pages showing basic information, relationship status, education, work history, interests. A wall where friends could post messages publicly, private messaging being available, photo albums being uploaded and tagged, the tagging feature being clever, letting you identify people in photos, those people being notified, the social pressure to create and maintain profile being strong. Not being on Facebook, meaning missing out on social connections. The network effects being powerful motivator. The interface being clean initially, relatively uncluttered, the news feed launching in 2006, showing updates from friends in one place rather than requiring visiting each friend's profile. The aggregation being convenient but also controversial initially. People objecting to their updates being broadcast, the privacy implications being unclear, the company adjusting settings after backlash, the evolution being gradual, the platform learning from user reactions. The experience being about genuine social connection initially rather than algorithmic content feeds, chronological timelines showing everything friends posted, no filtering, no curation, except what you chose by friending people. The raw stream of updates being manageable when you had 50 or 100 friends, becoming overwhelming when networks grew to hundreds or thousands, the algorithmic feed becoming necessary according to Facebook, though the filtering meaning you miss many friends' updates, the trade-off being debated. YouTube launches in 2005, 3 former PayPal employees creating the platform, the first video being me at the zoo, 18 seconds of co-founder Jawed Karim at San Diego Zoo. The mundane subject being fitting for platform about user-generated content, the tagline being broadcast yourself, the platform enabling anyone to upload videos, share them with the world, the democratization of video distribution being revolutionary, no longer requiring television networks or film studios to reach audiences, just a camera, internet connection, and something to say, the barrier to entry being lowered to nearly zero. The explosion of user-generated content being immediate, massive, diverse, everything from amateur music videos to educational lectures, to comedy sketches, to personal vlogs, to makeup tutorials, to gaming streams. The variety being endless, the long tail being very long. A few videos getting millions of views, most getting dozens or hundreds, but everyone having equal access to platform, the discovery algorithms determining what becomes popular, the recommendation engine being powerful, suggesting what to watch next, the suggestions being sometimes eerily accurate based on viewing history, engagement patterns, what similar users watched, the machine learning being sophisticated, controversial, the rabbit holes being real, one video leading to another, hours passing unnoticed. You find yourself uploading your first YouTube video in 2006, perhaps recording with a webcam, the quality being low, 320 by 240 resolution, the compression artifacts being visible, but the ability to share being exciting. The process being straightforward, clicking the upload button, selecting a video file from your computer, adding a title and description, choosing tags for searchability, selecting a thumbnail from frames in the video, waiting for the video to process, the encoding happening on YouTube's servers, converting your video to Flash format, for browser playback. The processing taking perhaps 10 or 15 minutes depending on video length and current server load. Then the video being live, accessible to anyone with the link, potentially being viewed by millions if it goes viral, though statistically being watched by dozens or hundreds, but the possibility being thrilling. Twitter launches in 2006, Jack Dorsey's idea, the first tweet being, "Just setting up my TTR," the platform limiting messages to 140 characters, the constraint being deliberate, forcing brevity, the origin being SMS text, message length limits, the platform being designed for mobile from the start, the short messages being called tweets, the metaphor being birds chirping, quick short messages rather than lengthy posts, the format being perfect for quick updates, sharing links, having conversations, the threading being basic initially, later being improved, the real-time nature being appealing, seeing what's happening now, the sense of immediacy being addictive, the language of Twitter emerging organically, users inventing mentions for addressing specific people, hashtags for topical categorization, RT for retweeting others' messages, the company adopting these user innovations, making them official features, the community-driven evolution being characteristic of early social media, users finding creative ways to use limited tools, the constraints breeding creativity, the timeline being chronological initially, showing everything from accounts you follow, the experience being like having a window into thousands of people's thoughts simultaneously, the stream of consciousness being overwhelming but fascinating, the addiction being real, the constant checking being habit, the FOMO, fear of missing out, being powerful motivator, the real-time nature, meaning events unfold on Twitter, news breaking on platform before traditional media, the shift of information flow being significant, journalists monitoring Twitter for stories, the platform becoming primary source for breaking news, the verification being problematic, false information spreading as quickly as true, the corrections being slower than initial viral spread. Instagram launches in 2010, Kevin Systrom and Mike Krieger creating the app, being mobile only initially, iPhone exclusive for first years, focusing on photos, applying filters to make them aesthetically pleasing, the vintage filters being popular, the square format being distinctive, reminiscent of Polaroid instant photos, the nostalgia being deliberate, appealing to desire for authenticity despite being heavily filtered, the contradiction being unnoticed or accepted, the aesthetic being part of the appeal, making everyone's photos look better, the democratization of photography being similar to Instagram's democratization of video, the ease of sharing being the key, taking a photo, applying a filter with one tap, adding a caption, posting to your followers, the whole process taking seconds, the simplicity being elegant, the friction being removed, the instant gratification being satisfying, the likes appearing quickly, the validation being psychological reward, the dopamine hit being real, the addiction being by design, the infinite scroll being deliberately addictive, the psychology being understood and exploited by designers who studied behavioral psychology, the engagement metrics being optimized, the user retention being primary goal, the platform's success being measured by time spent. The more time, the better from business perspective, the user's well-being being secondary to engagement. The shift from desktop to mobile, accelerating through these platforms, smartphones being the primary way people access social media, the always available nature being key to adoption, checking Facebook while waiting in line, watching YouTube videos during commute, tweeting from anywhere, Instagram being mobile only for first 2 years, the design being touch first, the interaction models being native to mobile rather than adapted from desktop, the platform shift being complete, mobile internet traffic surpassing desktop, the assumption being that users are on phones, the design following. The algorithms emerge gradually, platforms initially showing chronological feeds, everything your friends or follows posted appearing in order. But as user bases grow, as people follow hundreds or thousands of accounts, the chronological feed becomes overwhelming. Too much content to see everything. The platforms introducing algorithmic curation, showing what they think you want to see based on engagement, likes, comments, shares, time spent viewing. The machine learning models optimizing for engagement, keeping users on platform longer, showing content likely to generate reactions. The controversy being that engagement and quality aren't the same. Inflammatory content generating strong reactions, thoughtful content being overlooked, the incentive structure favouring outrage over nuance. The viral content phenomenon becoming central to internet culture, videos or images or ideas spreading exponentially, doubling in views every few hours, reaching millions within days. The network effects being dramatic, each share exposing content to new audiences who might share it further. The growth being exponential when it catches on, though most content never goes viral, the distribution being extremely unequal. Winner-take-all dynamics, where a few pieces of content get massive attention while most get none. Remember those early web pages with visitor counters and guest books? Now platforms like YouTube serve billions of videos daily, Facebook connecting 3 billion users, the scale being incomprehensible, the infrastructure required being massive, data centers worldwide, content delivery networks caching popular videos, databases tracking friendships and follows and likes. The engineering challenges being substantial, the solutions being sophisticated, distributed systems handling traffic that would overwhelm single servers, the scalability being achieved through careful architecture, years of optimization, continuous refinement. You now find yourself contemplating the Internet's security infrastructure, the ongoing battle between attackers and defenders, the arms race that never ends, each side adapting to the other's tactics, the techniques becoming increasingly sophisticated on both sides, the stakes rising continuously as more valuable information moves online. Banking and commerce and personal communications and medical records and government systems all depending on secure connections. The encryption being essential, the trust infrastructure being critical, the failure potentially being catastrophic. SSL and its successor, TLS, encrypt web traffic. The secure sockets layer being developed by Netscape in the 1990s, transport layer security being the standardized successor, HTTPS replacing HTTP, the S standing for secure, the padlock icon in browser address bars indicating secure connections, the visual indicator being important, training users to look for it before entering sensitive information, the encryption preventing eavesdropping on the connection, protecting passwords and credit card numbers, and private messages from being intercepted by anyone monitoring the network, the cryptography being strong, using key lengths that would require millions of years to break by brute force, the mathematics being sound, the implementation being carefully reviewed by cryptographers worldwide, the security depending on both strong algorithms and correct implementation. The bugs in implementation sometimes undermining strong crypto, the eternal vigilance being necessary. The certificate system creating chain of trust, certificate authorities being organizations trusted to verify website identities, issuing certificates that browsers trust, the root certificates being embedded in operating systems and browsers, the trust being transitive. If you trust the CA and the CA trusts the website, then you trust the website, the logic being simple, but the implementation being complex, the certificate containing the website's public key, the CA's digital signature proving the certificate is legitimate, the browser verifying the signature, using the CA's public key, the math working because of properties of public key cryptography, RSA or elliptic curves, enabling encryption without sharing secret keys. The certificate management being largely invisible to users, but critical infrastructure for secure internet, websites obtaining certificates from authorities like Let's Encrypt, which revolutionized certificate issuance by making it free and automated, or traditional CAs like DigiCert, Sectigo, GoDaddy, which charge fees but offer insurance and support. The certificates expiring after periods ranging from 90 days to 2 years, requiring renewal before expiration, webmasters monitoring expiration dates carefully, setting reminders, automated systems handling renewals, the ACME protocol enabling automatic renewal, the failure to renew causing site outages, visitors seeing scary browser warnings about expired or invalid certificates, the user experience being broken, trust being lost, the importance being clear from the disruption when certificates expire, the monitoring being essential, the renewal being boring but critical maintenance task. Firewalls filter traffic at network boundaries, sitting between networks, examining packets, the stateful inspection tracking connections, allowing replies to legitimate requests while blocking unsolicited incoming traffic, the rules being configured by security teams, balancing access requirements with security constraints, blocking known malicious IP addresses from threat intelligence feeds, limiting exposed services to only what's necessary, logging suspicious activity for later analysis, the defensive posture being layered, defense in depth being principal, multiple controls providing overlapping protection, no single control being perfect, the combination being effective against most attacks, the security being probabilistic rather than absolute, reducing risk rather than eliminating it, the acceptance of residual risk being necessary, perfect security being impossible, the goal being adequate security at acceptable cost. VPNs create encrypted tunnels through untrusted networks, the virtual private network being like a secure pipe through dangerous territory, useful for remote access to corporate networks. Employees working from home, connecting to office systems, also increasingly used for privacy. Consumers using VPN services to hide traffic from ISPs and websites, appearing to originate from VPN server rather than actual location. The encryption protecting against local network eavesdropping on coffee shop Wi-Fi. The use cases being both corporate and consumer. The technology being the same, the motivations being different. Enterprises wanting to extend their network securely, individuals wanting privacy and accessing geo-restricted content. The streaming services blocking VPNs being ongoing cat and mouse game. Distributed denial of service attacks remain persistent problem. Attackers using botnets of compromised IoT devices, security cameras and routers with default passwords, sending traffic to flood targets, overwhelming servers or network connections, legitimate traffic being unable to get through because capacity is exhausted, the defense being difficult, distinguishing attack traffic from legitimate requests being challenging when attacks are sophisticated, simple rate limiting helping, but also potentially blocking real users during viral events when legitimate traffic surges. The solutions involving specialized DDoS mitigation services from companies like Cloudflare and Akamai, massive bandwidth to absorb attacks, sophisticated filtering to identify attack patterns, anycast routing, distributing attack traffic across many servers worldwide, the cat and mouse game continuing endlessly, attackers adapting as defenses improve, attack techniques evolving, amplification attacks using reflection off misconfigured servers to multiply traffic, the problem being partly technical and partly social, the solutions requiring both better technology and better security practices by device manufacturers and network operators. Privacy concerns grow as internet becomes central to life. Companies collecting vast amounts of data about user behavior, browsing history, search queries, locations tracked through smartphones, social connections mapped through friend lists and communication patterns, the surveillance being extensive, though often invisible. The business model of many internet services being advertising, free services supported by showing targeted ads, requiring detailed user profiles to target ads effectively. The more data collected, the better the targeting, the incentive being to collect as much as possible, track users across sites, build comprehensive profiles, the creepiness of ads following you around the web being evidence of cross-site tracking, the cookies and tracking pixels, and browser fingerprinting enabling persistent identification even when users try to avoid tracking. Regulations emerge attempting to protect privacy. GDPR, General Data Protection Regulation, in Europe requiring explicit consent for data collection, giving users rights to access their data, delete it, port it to competitors, the fines for violations being substantial, percentage of global revenue enough to get companies' attention, the cookie consent banners appearing on every website being visible. Consequence, the annoying clicking through consent dialogues being price of privacy protection, the effectiveness being debated, whether users genuinely understand what they're consenting to being questionable, whether companies comply in spirit or just letter of law being uncertain. The implementation being imperfect, but the attempt being important, establishing principle that users have rights to their data, that consent is required, that transparency is mandatory. Data breaches reveal security failures, major companies losing customer data to hackers, millions of records being stolen, passwords and credit cards and personal information being exposed, the disclosure requirements forcing companies to admit breaches, the reputational damage being substantial, the class action lawsuits following, the cost of inadequate security becoming clear. The industry slowly learning that security can't be afterthought, must be designed in from the beginning, the cultural change being gradual, security engineering being increasingly valued, the investment being justified by avoiding breaches. You find yourself drifting towards speculative futures, contemplating where the internet might go, the technologies being developed, the possibilities being imagined, the uncertainty being high, predicting technology being notoriously difficult, the future being influenced by technical possibilities, economic incentives, regulatory frameworks, social adoption patterns, the interplay being complex, outcomes being unpredictable. Web3 proposals. Imagine decentralized internet based on blockchain, removing centralized control, users owning their data, the vision being appealing to those concerned about tech company power. The technical challenges being substantial, blockchain scalability being limited, energy consumption being high, user experience being poor compared to centralized alternatives, whether Web3 becomes mainstream or remains niche being uncertain, the debate being active, believers being enthusiastic, skeptics being numerous, the outcome being undetermined. Quantum networking promises unhackable communication through quantum key distribution, the physics making eavesdropping detectable, the technology being demonstrated in labs, small-scale networks being deployed, whether it scales to internet-wide deployment being unknown, the engineering challenges being immense, the investment required being substantial, the timeline being measured in decades, the possibility being real but distant. Artificial intelligence increasingly browsing internet, agents searching and summarizing and analyzing, the autonomous systems being more sophisticated, the line between human and AI internet usage blurring, the traffic patterns changing, the detection becoming difficult, where the future internet is primarily human to human or machine to machine being open question, the evolution being ongoing. 6G cellular networks being researched, promising even higher speeds than 5G. Terahertz frequencies being explored, the propagation characteristics being challenging, the range being very short, the density of base stations required being high, the deployment cost being enormous, whether it happens at all being uncertain, the marketing preceding technology by years, as always with cellular generations. Satellite constellations like Starlink attempting global coverage, thousands of satellites in low Earth orbit providing internet anywhere, the coverage being attractive for remote areas, the latency being lower than geostationary satellites, the capacity being limited by satellite technology, whether they can compete with terrestrial fibre and wireless being questioned, the service being expensive initially, the market being uncertain, the investment being massive, the outcome being unknown. It is late now, very late, the clock showing past midnight, most of the world sleeping while infrastructure continues working. The story is nearly over, the history traced from ARPANET's 4 pioneering computers to billions of connected devices, from 50 kilobit phone lines to terabit fibre optic cables, from academic research network to global platform connecting half of humanity, the journey being remarkable, the transformation being complete, profound, the internet being infrastructure as essential as electricity or water, taken for granted by most, its presence being assumed, noticed only in its absence, the dependency being total. You stand in a data center at night, having been given special permission to visit, to walk the aisles alone, to observe the infrastructure that makes the digital world possible. The visit being quiet, reverential almost, like visiting a cathedral, the sense of being in the presence of something important, something larger than yourself, the scale being impressive, the room being vast, a warehouse-sized space filled with equipment, rows of server racks extending into the distance, the perspective making far rows seem to converge toward a vanishing point, the geometry being hypnotic. The lights are dimmed for night operations, the overhead fluorescence being turned off or reduced, only emergency lighting and equipment LEDs visible. The hundreds of thousands of status lights on equipment creating a field of blinking stars, green and amber lights pulsing in patterns, each blink representing data flowing, packets being routed, connections being established, requests being processed, and responses being sent. The visual representation of digital traffic being strangely beautiful, hypnotic, mesmerizing, the rhythm being complex but regular, impossible to follow individually but collectively, creating impression of constant coordinated activity, of tireless work, of infrastructure functioning reliably, hour after hour, year after year, decade after decade. The floor beneath your feet is raised, perforated tiles covering the plenum space where cold air is distributed, your footsteps making hollow sounds on the tiles, the acoustic being distinctive, different from solid floors, the empty space beneath being palpable, the air movement being felt through the perforations. Cool air rising, being drawn into servers, exhausting as hot air, the thermodynamic cycle being continuous, energy being converted to computation and heat, the heat being removed, the cycle repeating endlessly, the physics being inescapable, the engineering being sophisticated response to fundamental constraints. The sound is the constant hum of cooling fans, thousands of them spinning continuously at various speeds, moving air through servers and network equipment, removing heat from CPUs and memory chips and power supplies, the collective sound being substantial but not deafening with ear protection, more a deep, steady hum than a roar, the white noise being loud but consistent, the kind of sound that becomes background after exposure, the brain learning to filter it out, the constancy being almost restful after initial overwhelming impression, like rain on a roof or waves on a beach or wind through trees. The mechanical sound becoming somehow organic in its consistency, its regularity, its patient continuation regardless of human awareness. The temperature is cool throughout the space, maintained carefully at optimal temperature for equipment longevity, perhaps 68 degrees Fahrenheit in the cold aisles, warmer in the hot aisles where equipment exhausts, the climate control being precise, sensors monitoring temperature and humidity continuously. The HVAC systems adjusting constantly, maintaining stable conditions, the air being dry, filtered, clean, the environment being optimized for electronics rather than human comfort, the coldness being slightly uncomfortable if you stay too long, but for a short visit being refreshing, clarifying, the contrast with outside air being noticeable, the artificial environment being obvious, purpose-built, controlled. A lone technician walks down a distant aisle, flashlight beam visible, checking equipment temperatures with infrared thermometer, the IR sensor being pointed at components, the readings being recorded on a clipboard, the routine inspection being part of continuous preventive maintenance, the vigilance being how reliability is achieved through constant attention, catching problems early before they cascade, before they affect services, before customers notice, the unglamorous work of infrastructure being essential, the reliability depending on people who check servers at 2 a.m., who respond to alarms, who replace failed drives, who maintain physical systems, the invisible work making visible services possible. The racks stretch in long rows, each rack containing perhaps 42 units of equipment, each unit being 1.75 inches high. The standard rack unit, the density being remarkable, each rack consuming kilowatts, generating equivalent heat, the power distribution being critical infrastructure, the electrical systems being redundant, dual utility feeds coming from different substations, diesel generators standing ready as backup, uninterruptible power supplies providing seamless transition during switchover, the batteries being substantial, forklift batteries in large installations providing minutes of runtime while generators start, the redundancy being expensive but essential, the cost of downtime exceeding the cost of backup systems. Somewhere above you, unseen in the ceiling space, fibre optic cables leave this building, routed through cable trays, exiting through conduits, running to telecommunications rooms, to carrier hotels, to internet exchange points, eventually connecting to the global fibre network, the long-haul cables crossing continents and oceans, the submarine cables being particularly impressive, thousands of kilometres of fibre on ocean floors, carrying terabits continuously, the physical network connecting continents, making the global internet possible, the light pulses travelling through glass fibre at speeds approaching light speed in vacuum, the delays being noticeable but small, the world being connected, distance being measured in milliseconds rather than miles. The story is ending now. The listener is drifting into sleep, the technical details fading, the sensory impressions remaining, the hum of fans, the blinking lights, the cool air, the quiet activity of machines working through the night, maintaining connections, routing packets, serving requests, the infrastructure being reliable because people made it so, because protocols were designed carefully, because engineers solved problems patiently, because the accumulated work of decades created something remarkable. Remember those researchers in 1969 typing LO before the system crashed? Remember the screech of dial-up modems? Remember the first websites with blue underlined links? The journey has been long, the transformation complete, the internet now being so embedded in life that imagining life without it requires effort. The younger generation never knowing a world before, internet taking connectivity for granted. the older generation remembering but barely, the memories fading, the present being so different that the past seems foreign. Somewhere right now, packets are flowing through cables, under oceans, bouncing through routers, being cached on CDN servers, reaching phones and computers and smart devices, carrying messages, videos, transactions, the invisible traffic being enormous, petabytes per second globally, the scale being incomprehensible, the system working because thousands of engineers designed it carefully, because protocols are robust, because infrastructure is redundant, because maintenance is continuous. The internet works silently, patiently, endlessly, connecting billions of people who will never meet, enabling collaboration between strangers, making knowledge accessible, transforming commerce, reshaping culture, changing everything while being invisible. The ultimate infrastructure being the kind that disappears, that functions so reliably that nobody thinks about it, that enables other things rather than demanding attention itself. Rest now. The servers will keep running, the packets will keep flowing, the network will maintain connections through the night. Somewhere data centers hum quietly. Somewhere cables carry light pulses across continents. Somewhere routers examine packets and forward them toward destinations. The great global network continues its patient work, tireless, invisible, essential. Sleep now, knowing that the system works, that the infrastructure is sound, that the network will be there in the morning, connecting you to the world, functioning quietly as it always does, the modern miracle being so reliable that it's boring, which is perhaps the highest compliment infrastructure can receive.